For our last section on weather and water, we're looking at upper air soundings and radio sonids. So as we're looking at weather balloon launches, we could see right here an animated graphic that's showing what happens when we launch a weather balloon. And it's going to give us some information about that weather balloon. So we can kind of see the graph as we go up through the atmosphere. We see the temperature going down. Okay. If we look at the air pressure, we see the same thing. As we go up, there's a decrease in air pressure, and the same thing with the dew point. And when we start to then compare the temperature and the dew point, that's where we start to get some of the useful information. So on these specific run of the weather balloon, we see the temperature here in red and the dew point in blue. And where the temperature and the dew point overlap, that's where we're going to see clouds forming when the temperature and the dew point meet. If we look at another location, we could look at Phoenix and compare that with Chicago. Okay, when we look at the air pressure, they're almost identical. As they go up, there's a decrease in air pressure. Same thing with temperature. As we go up, we see a decrease. Now we can see Phoenix here in the light red and Chicago in the dark red. There is a difference in temperature starting, but the same effect as we go up, temperature decreases, and the same thing with the dew point. As we go up, we see that dew point going down and getting lower. So when we look here for Phoenix, we never see a point where the temperature and the dew point overlap, so we don't see any clouds on that day in Phoenix, but we do for Chicago. Looking at the worksheet that went along with the activity that we just looked at, has here a couple questions about what happened as we go up higher in the atmosphere. We see a decrease in the pressure in both places, like we've seen on the graph. Okay, the trends of temperatures for both cities, again the same thing. As we go up, they decrease. Okay, most importantly, we get down here to number 4 and to number 5. With number 4 and number 5, these are the important ones. This is where we're going to get the interesting information from the weather balloon soundings. As we go up through the atmosphere in Chicago, we were able to see the temperature and the dew point overlap. Because the temperature and dew point overlapped, right in here, we will see clouds forming on this day in Chicago. Now, when we look at Phoenix, okay, the dew point is always higher, or sorry, the dew point was always higher, that's backwards there. It should be the temperature was always higher than the dew point in Phoenix, so the lines never crossed. Needless to say, we never seen the light red line and the light blue line ever cross or touch, so we don't see any clouds forming that day. If we scroll down here, we can look at a couple other places. Here's again our Chicago. Okay. Illinois, so we can kind of see this overlapping here where we have clouds forming at a few different spots. Okay, if we look at Boston for a separate one here, we could see for Boston, right in here we see an overlap, and again up here we see an overlap, so we would see clouds forming in Boston. Okay, Phoenix we've already looked at, but again, just to point this out, because we see this gap between them, where the temperature and dew point never cross, never meet, never overlap, we're not going to see any clouds forming. And we can come down here to our last example in San Francisco. Right in here, we see a little bit of an overlap, so we would have clouds forming very low. Okay. This transitioned us now to start to look at the different types of air masses and what happens when those air masses collide. So we started to look at cold fronts. Okay, and this would be an example of a cold front where we have a relatively quick change from warmer air mass to a colder air mass, and it gives us these cumulonimbus type clouds, which are going to bring on heavy storms, more violent weather, stronger winds, as opposed to our warm front where we have a much larger change. Okay, with the cold front it was 500 kilometers, now with the warm front we're looking at 1,000 kilometers. And we see it's a more gradual change. These are generally, with a warm front, the type of days where it's going to be rainy all day, not so much heavy rain, but a steady rain or even an on-off drizzle all day long, or maybe even a little bit longer than a day, as it takes a lot more for this warm air to get the cold air to move out of the way. And we could see the shape of the front has also changed, more of a wedge. When we go back up to the cold front, much more abrupt change, a lot more vertical, more of a scooped look to this. The cold air is doing the pushing. That's why we're calling this one a cold front. It's moving the warm air out of the way. And down here we see just the opposite. The warm air is the stronger air mass. And that's why it's a warm front. It is pushing the cold air out of the way. This allowed us to transition into the next topic that we looked at, which was how lightning is created. When we look at this topic of how lightning is created, we're kind of looking at the cumulonimbus clouds that we just talked about associated with cold fronts. So for that to happen, we need this separation of the charged particles to take place, and then once we get that, we're going to start to get these different charged particles lining up, like it says here, a field generation, and we're going to start to get really what we look at here is cloud to ground lightning. We kind of look at the steps that take place in this cloud to ground lightning. Okay, we need what we call streamers coming down out of the sky towards the earth. And these streamers are not lightning bolts. This is the negative charge from the cloud trying to complete a path to the positive charge so that a lightning bolt then could follow that path. Coming up from the earth, we're going to have these step leaders. Okay, and we're going to have these different particles moving closer together. Okay, so as we have these particles moving closer together, I think I misspoke before when I said it's supposed to be these step leaders coming down out of the clouds and these streamers coming up from the ground. So the step leaders coming down from the clouds towards the ground and these streamers coming up from the earth. So finally, as that path is kind of connected there and the circuit is kind of complete in that way, we then have what we call the return stroke, and this would be our bolt of lightning, and this moves very quickly from the ground up to the cloud. So remember that the bolt of lightning that we see, while it doesn't appear that way, does go from the ground up to the cloud. Okay, we could see here on the right in this high-speed image the step leaders coming down from the clouds, and we will then see a complete path being made, and we can see tiny little streamer coming up from the ground there, and then that bolt of lightning going back up. If we look very closely, there are a couple other slow motion examples of these lightning. So we can see here in figure 2 as we can kind of watch these step leaders coming down to the streamer right there, and that return stroke, where that's the bolt of lightning. Okay, and again here in figure 1 you can see the same thing happening with that bolt coming from the ground up. Figure 3 does a nice job of showing this as well. You can see the bolt going up and then back into the cloud, and it's again moving from the ground up to the cloud. And finally, for this section, we looked at the sound of thunder. So associated with that bolt of lightning is also going to be a loud crack of thunder. So with this loud crack of thunder, we're looking at rapidly heating up air to about 5 times the temperature of the surface of the sun, which is going to cause that air to expand, and it's going to expand what we call explosion expansion, which is going to result a shock wave similar to a sonic boom and exploding fireworks. So that shock wave is going to kind of start off like it's showing here in the pictures from a few different parts in the lightning bolt, and even though the bolt is gone, the sound wave is still going to be traveling. The reason why we see the lightning bolt and then hear the thunder is that sound is traveling much faster than the light is traveling much faster than the sound through the air. So that it's like going to a baseball game, and at times you can see the ball coming off of the bat and then hear the ball being hit by the bat. The light is going to travel much faster than sound, and that's why we get the bolt of lightning and then we hear the thunder afterwards. And I'm going to stop here for this first video, and then I'm going to pick up with the second part, which is going to be climate warming and looking at weather maps.